Hey, this is Math 8, Unit 8, Lesson 14. This is actually the last lesson I'll be doing from all the series of Math 6, 7, and 8. Decimal representations of rational numbers. So first of all, we have a notice and wonder. What do you notice? What do you wonder? I notice these are all the fraction bars. We can see that they're divided into sections quite evenly. For example, this is 2 even sections, 4 equal sections. This one is 8. Each one seems to also become double, like this has 2, this is 4, this is 8. I can guess this is probably 16. We can make them into fractions, 1 out of 2, 1 out of 4, 1 out of 8, based upon what's shaded there. Those are some things you might notice and might wonder about these things. We have equal parts, we have fractions. If the whole thing is a whole, it could have a value of 1, so it becomes a half, but that's just kind of guessing what that could mean there. Alright, let's take this idea here, and we're going to take this idea of cutting things in half and move into having the length right here on this first activity. It says mark the midpoint between 0 and 1, and what is the decimal representation of that number? So if we mark a midpoint right here, the decimal between 0 and 1 is 0.5. Now, it says mark the midpoint between 0 and the new point. Well, that midpoint would be here. And what's between 0.5 and 0? It's 0.25. Okay? And if you weren't sure about that, think about this being something like 50, right? What's half of 50 is 25. Now the next thing it says, do it again. So we put one here, and this becomes 0.125. Again, you might think, how'd you get there? Well, put a 0 there real quick, and what's half of 250? 0.125. So what do you see happening every time we're adding a new midpoint? Okay, every time we add a new midpoint, we're seeing that the value keeps halving, right? It's cutting in half every time. It's something we keep seeing by doing this. We cut it in half, cut it in half, cut it in half. But also notice that as we do that though, the number of digits increases by 1 each time. Here we had 0.5 with 1 digit, 0.25 with 2, and 0.125 with 3. We can imagine that if we cut this in half right there, what do you think would happen? You'd probably have a decimal and 1, 2, 3, 4 decimal places right there. Okay, it's just a guess. Let's take a look at what does happen. I don't actually know. I don't know what the answer is. Let's just see. So if I do 0.125, okay, and I divide that by 2, we get, hey, look at that, 0.0625. So yep, you end up with 4 digits right there, and that's how we cut that in half, just like that. Okay, interesting. Okay, so value keeps halving, digits keeps growing. All right, we already did that, cut it in half, and we talked about that one on the front page. So moving on to 14.3, recalculating rational numbers. Rational numbers are fractions and their opposites. All these numbers are rational numbers. Show they're rational by writing them in the form of a over b or negative a over b. So we want to turn these decimals and radicals into fractions. So 0.2 is the same as 2 tenths. Now we have it as a fraction, showing that it is a rational number. Remember, the key word in rational is ratio, right? And that's what a fraction is. It's a ratio, 2 out of 10. Now this one, let's look at this part first. The square root of 4 is 2. Now it's negative, so we keep a negative there. Is that a ratio? No. But we also know that we could do this. Now it is. Any number over 1 is a fraction. And I can write over 1, it stays the same, so it's negative 2 over 1. C is a great one. You might be thinking to yourself, well, I'm not sure. I mean, do I write down 333 over 1,000? I guess you could. But one thing you learn through time is that when you see 0.3 and repeating like this forever and ever and ever, just keeps repeating like this, it actually is one that you should be familiar with, which is 1/3. And you could see that if you took 1 and you divided it by 3, what you'd find is that 3 goes into 1 0 times, goes into 10 3 times. So you have a 1, bring down a 0, goes into 10 3 times, goes into 10 3 times, and it just goes on forever and ever and ever. So 1/3 is actually what that's going to be. This one here is the cube root of 1,000, and we know that the cube root of 1,000 is 10, but we want to write it as a fraction. Okay, so we write it in the form of a over b, so we'll make it like letter b, we'll do 10 over 1. On the next one, we could think of it like this. First, you could think, if you wanted to, that you have a negative 1 in front. Awesome. Now you have this other fraction part, which is going to be 1 out of, and we have 10, 100, 1,000, 10,000, 100,000, millionth. So 1, comma 1, 2, 3, comma 1, 2, 3. But we want to write this in the form of a over b, so I need to put this one on top of that, which means this 1 is a whole one of those plus one more, meaning we have 1 million, 1, 2, 3, 1, 2, and 1. It's negative, all over 1, 1, 2, 3, 1, 2, 3. So that becomes the fraction form there. And the last one, the square root of 1 is 1, the square root of 9 is 3. And that's all there is to that one, okay? And that's it. So we rewrote each of those rational numbers in a different way. Okay, let's take a look here at number activity 2, or number 2 for that part. It says all rational numbers have decimal representations too. Find the decimal representation of each of these rational numbers. So if we have 3 over 8, that's like doing 3 divided by 8. I put a decimal point there, a decimal point there right away, and then we see what we have. I can add some zeros to hold some spaces. 8 goes into 3 0 times. 8 goes into 30 3 times. 3 times 8 is 24. We subtract and we have 6, bring down the 0. 8 goes into 60 7 times, so we have 56. We have 4 there, bring down the 0. 8 goes into 40 5 times, so 3/8 is the same as 0.375. How about 7/5? Well, 7 goes there, 5 goes there, put a decimal, and some zeros. Put my decimal up right away before I start dividing. 5 goes into 7 one time, so we have 5 here. 7 minus 5 is 2, bring down the 0. And then 5 goes into 24 times, so we end up with simply 1.4. On our next one, we actually have, it's pretty easy here, it's a thousandths, so we can rewrite that as 0.999, and that's all there is to that one. For D, I have 111, and we're going to divide that by 2. So 2 goes into 1 0 times, goes into 11 5 times. So we have to subtract, we have to bring down that 1. It goes into that one 5 times. 5 times 2 is 10. We bring that down, we put a decimal and a 0, bring a 0 down now. It goes into 10, in this case here 5 times, and we're done. So we have 55.5. And our last one, cube root of 1 is 1, cube root of 8 is 2, but as a decimal that's 0.5. Okay, just a little practice using some arithmetic there, and that's the idea. This last activity is called zooming in on a number, and what it wants you to do is we're going to take this number, we're trying to figure out where exactly is 2 11ths. Now what I did first of all is I said, well, let's just see what 2 11ths is. 2 11ths is 2 divided by 11, and what we can see is we're going to get some repeating numbers here. Ready? 11, put decimal up, 11 goes into 20 one time, so we have 11 right there. Subtract and we have 9, we bring down the 0 and we have 90. 11 goes into 90 8 times, so we have 88, and 90 minus 88 is 2, we bring down the 0, and we're right back to where we started, back with a 20, aren't we? So we have a 1. 1 times 11 is 11, we subtract, we have a 9 again, bring down the 0, and we're back to an 8. And what we see is that this continues to repeat again and again and again. When we write this out, we would actually write it as 0.18, and we put this bar over the 1 and the 8 because that part is going to continue to repeat forever and ever. So on this line here, we can write 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9, and recognize that 2 11ths is going to be between 1 and 2. Okay, we know it's at least about 0.1 and a little bit more. So 2 11ths is going to go right about there. Oops, I don't know what that number is. So now if I take this 0.1 and put it right here, 0.1 and add a 0, and put the 0.2 here and add the 0, Now I can fill in these values at 0.11, 0.12, 0.13, 0.14, 0.15, 0.16, 0.17, 0.18, 0.19. Okay, so now where is 2 11ths here to kind of make it get a little bit closer? Well, it's at 0.18. So it's going to be right about here and a little bit more. So it's going to go there. Okay, so now we're going to take this value, and that's 0.180, and the second value, 0.190, and we'll fill in these. We have 0.181, 0.182, 0.183, 0.184, 0.185, 0.186, 0.187, 0.188, and 0.189. Again, our next value we had was 0.181, so put it somewhere about here. Okay, so it's kind of making that point jump from place to place. And we can continue by putting this one here, this one there, and we'd see where it went, which we know it ends up going to 0.1. So it's going to go somewhere here, about, that's a 9, so somewhere about there, in that case there. We can continue this for a long time, zooming in, and we can keep on going, but we're going to find that the more we zoom in, the more it just keeps on going on forever and ever and ever. Okay, so that's repeating that step again and again, which is what it said to do in our directions, right? In the top line, we labeled the tick marks, we found the first decimal place, and we estimated where 2 11th was going to be. We did it on the second number line as well, and kept estimating, and we added arrows to the third number line, and we kept going for the remaining number lines. So what do we think a decimal expression is going to be? What we saw was we got 0.181818, and it kept going on and on. The way we write that, though, is as soon as we get something repeating, we can put this repeating bar over the top, which tells people that this value is going to continue to go on, and you don't have to put the dot. This tells you this is an irrational number that never has a stop. It just keeps on going forever and ever and ever. Okay? So that is the idea behind that one right there. So in summary, we learned earlier that rational numbers are a fraction or the opposite of fraction. So rational numbers are a fraction or the opposite. For 3/4 and -5/2, they're rational. A complicated looking numerical expression can also be a rational number as long as the value of the expression is a positive or negative fraction. For example, square root of 64 and the negative cube root of 1/8 are rational because square root of 64 is 8 and this happens to be -1/2. Rational numbers can also be written using decimal notation. So rational numbers can be written with decimals. Okay. Some, though, have what we call a finite decimal, right? They just stop. And others have an infinite decimal, where they just repeat forever. And that's what the infinite decimal means. They go on forever. When you have a number like this, the bar over that part of the expression tells us the part which is going to repeat forever and ever. Okay? And when you have that, then that's going to make them be not quite as nice. Okay? A little more challenging to work with there. Alrighty. So that is really it. We're going to leave that for now. We're going to pause and yeah. All right, and we'll come back and check your homework here in just a second. All right, here we go. The last homework for me for the year. All right, Andre and Jada are discussing how to write 17/20 as a decimal. Andre says he can use long division and divide 17 by 20 to get the decimal. He can do 17 divided by 20 and he can get the decimal. True, he could. Jada says she can write an equivalent fraction with a denominator of 100 by multiplying by 5/5. So 17/20 times 5/5, and we get 100 on the bottom, and we figure out that's going to be there. Okay, and then rewrites the numbers hundreds as a decimal. Do these strategies work? Yes, they both work just fine. Which do you prefer? Well, it depends. Do you like doing long division or a simple math problem here? I prefer this one myself because it's 17 times 5, and 17 times 5 gives me 85. Okay, so I like that because that becomes 85 over 100. So as a decimal here, that becomes just simply 0.85, and I'm done. That takes me less time than it does to say how many 20s are in 17, 170. Granted, that is just as fast sometimes too, but that's what I prefer. All right, number 2, write each fraction as a decimal. Okay, so we're square rooting, so we're thinking about what times what gets you to 9. That's 3, and that's 10, because 10 squared is 100, 3 squared is 9, so we have 3/10. As a decimal, that's 0.3. Here, 99 out of 100 is 0.99, 99 hundredths. Square root of 9 is 3, square root of 16 is 4, 3/4 as a decimal is 0.75. And our last one, we have 23 over 10. You could think of it as writing it as 2 3/10 because 10 goes in here 2 times, right? So as a decimal, then that becomes 2 3/10, like so. Number 3. Write each decimal as a fraction. Okay, so here we have the square root of 0.81. Well, I know that 0.9 times 0.9 equals 0.81. So the square root of 0.81 is 0.9, but I want to get that into a fraction form, so that's the same as 9/10. Over here, I don't know about 276, so I'm going to write 276 out of 10, 100, 1,000, 10,000. So I write it like that, and we're good to go. Square root of 0.04 is going to be equal to 0.2, because 0.2 times 0.2 equals 0.04. Alright, now as a fraction though, because I want a fraction, that is 2/10. I can reduce that and say it's 1/5, and that'd be okay. And the last one here, I could think of it as 10 and 1/100th, but I want it as a whole fraction, so 100 times 10 is 1,000 plus 1, so times that plus that, so we have 1,001 over 100 for that one there. Number 4, find the positive solution to each equation. If the solution is irrational, write it using square root or cube root notation. Okay, so for A we have x squared equals 90, so this becomes the square root of 90, and I just leave it like that. That's all I can do with it. This one is the cube root of 90. Okay, so we're going to have the cube root of 90, which again is just what it is. There's nothing I can do with that one. Okay, alright. Square root of 1 is 1. Cube root of 1 is 1. They do the square root of 36, which happens to be 6. And the cube root of 64 ends up being 4. And finally, our very last one, here's a pyramid, and we can see we have the pyramid here, and we have the legs, we have the 15, and we have this length there, and then we have the L value they want us to find, so we have a nice triangle happening right there. Now, this is the center point of the pyramid. That means that the middle point is going to be about halfway, meaning this has a leg length of 8 already. So to find the measurement of the slant height, I would take 8 squared plus 15 squared and set that equal to, in this case here, L squared. 8 squared is 64, 15 squared is 225, so the L squared is there. We combine those together and we have 289 equals L squared, which means the square root of 289 equals L. Square root of 289 is not one I'm familiar with, but I did look it up real quick and I found that it was equal to 17. So we have a face here of 17 as the height of that triangle right there. So for the last question, it wants to know what's the surface area of the pyramid. The surface area is combined of the base here, which is a 16 by 16 base. 16 by 16 is 256, that's the area of that. And then I have all the triangles. The triangle has a base of 16 and it has a height of 17. So the triangle, and there's 4 of these by the way, don't forget, is 1/2 of the base times the height and then I can say times 4 because there are 4 of them there. So half of 16 is 8 times 17 times 4. 8 times 17 ends up being, I'll make a notes here real quick, ends up being 136, I'll double check. Oops, turn that on. So 8 times 17 equals 136, and 136 times 4 equals 544. So the combined area of the 4 triangles plus the base is going to equal 800, whatever it is, units squared. Okay? And that becomes the area of that. That's it for today, and that's it for our lessons for the year. Hope you've learned a little bit, and I guess tell your friends about how it helped you, so next year they'll keep watching and subscribing to Mr. Morgan's YouTube channel. Have a great day, have a great summer, great year. Bye.